So a lot of people ask me, for what purpose do you keep all this old hardware stuff? And for what are you collecting these old hardware computers? Like 486 running DOS, and what can somebody actually do with this in 2019? So I'm about to build a vintage computer, another vintage computer with a Z80 CPU. And as you might know, to control the memory chips, to tell when RAM is enabled, when ROM is enabled, you need to have some glue logic and or XOR and such things. And you might go about and implement these with these TTL devices, each logic function with a separate device. And this is quite hard to do, and when you're done, you can change it easily. Another possibility is use one of the programmable devices, like the PAL devices. In this case, they're named GAL devices. These are the ancestors of the FPGA devices. So the ancestors of the CPLD, and these support 5 volts input, so they are TTL and CMOS compatible. And you can drive the old glue logic stuff with these, and you can program logic functions into them. So it's much more versatile. And in order to program them, you need some programming hardware, like this Galblaster I built 2 years ago. And this Galblaster, there is a beautiful project in the internet. Actually, I can't remember the name of the author. Unfortunately, this is not done by me. The design was created by other people and modified by others. I reinserted the bus buffer chips. So this programmer is connected via a data cable. This is a standard parallel port data cable. And in order to program the devices, so the top sockets are not connected yet, so I had to put the chip into the sockets on the board here. So it's already inserted. To program these devices, the timing is very strict, and for this you need real-time operating system or a microcontroller. And since there is no real-time operating system, except on microcontrollers, you can't have things like real multitasking. It's not working in Linux either, because you need some microseconds accuracy. And for this purpose you can use the good old DOS. So here it runs on a 486 machine. This is the 486 machine. It just stopped working when I wanted to begin with the video, but the hard drive controller had a bad contact with the mainboard. So it took me a few seconds to fix this. And you can edit. First of all, we should have a look at the logic functions we want to implement in the design. And for this we open the function file, the PDS file, and I did a mistake here. As you can see, the ROM and the RAM chips are actually enabled when the device is either in boot or not in boot mode anymore. So this design switches banks. First it starts with the ROM as long as boot is active. Then with the first I/O request, as you can see here, the boot is made inactive. And with the inactive boot, the RAM is enabled instead of the ROM. And of course, the firmware has to copy itself into RAM before. So here's a mistake, because the Z80 CPU also issues refresh commands, and when it does a refresh, also A15 might be 0 or not 0, and we don't want to enable the RAM and ROM chips during a refresh cycle. This means we have to say that we don't want a refresh signal here at the same time, and we don't want a refresh signal here at the same time, and we don't want a refresh signal here. So let's call it refsh for refresh. And now luckily we have some pins not used yet, so pin 22 is can also be used. So we will tell the device, use pin 22 as an input, and we name it /refresh, and it is a combinatorial pin. combinatorial. Okay, that should do it. So we save this, and now we start Palasm. Palasm was created by AMD. This is version 1.5 of Palasm 4. We press a key, and then we can now load, retrieve existing design. Well, the current directory is wrong, change directory. So the GUI is rather complicated for nowadays standards. We first change the directory, and then we can retrieve. So we even don't have means of a file browser. We tell it we load text mode, and we open the PDS file we just edited, and then we press F10 to tell it the form is valid, and then we can view the design file, and we see the refresh we just added, and have another look at the function. So refresh must not be active, and then the thing is reversed for negative logic. Okay, then now we say run compile, and then the compiler runs. It actually runs faster than in DOSBox, astonishingly. And now he said he processed the file without any error, and we get a JDEC file. However, this JDEC file is for, as we can see the design file, a PAL device, and we need to convert it for a GAL device. So we exit this software, yes, I'm sure, and here we have another program. It's called Paltogal, and I run Paltogal, and I give it the file name, the JDEC file, and I'm just wondering about the date. Is it the correct date? 7413. And then I hit enter, and I see the conversion options, and here I can see 47 converts a PAL22V10 to a GAL22V10, so I enter 47, and then the output file name is Z80 control.jet, and then I can add a signature. I say this is ASCII, this is just the signature of the chip, and then it had converted my file. It has converted my file, Z80 control.jet. Yeah, the time and date is wrong, but it's consistent. So, and now I have to start Windows, and because the latest software, and the software was written in 2011, I think, for this old programmer, runs in Windows. So the voice of Spock is nice. So I start the Aftblast program, and I have to do this first because it initializes the parallel port, so that the program option is not enabled, and I can already load a JDEC file. First I have to select the device, and the device is a 22V10. Then I load a JDEC file, and I select C, and I select the Z80 directory, and then I choose my Z80 control, and then I switch on the device so it does not burn. That's good. And then I write the GAL. Write GAL till it turns red, and it's good again. I have a verify GAL. Verify OK! Wow, we have just programmed the GAL device, and we immediately switch it off. Well done! And now we can use the programmed chip in the Z80 design.